Good morning, students. Today we will continue our discussion on the topic of sensitivity analysis, which we have studied last time. So, the title of today's lecture is Sensitivity Analysis Part 2. The outline of today's talk is the various possibilities that could exist. We will take the same example that we had taken last time, and finally an exercise. As you know that sensitivity analysis means that if we make slight changes in the input parameters of a linear programming problem, what will be its effect on the final solution? Do we need to solve the problem all over again, or we can make some conclusions from the initial and the final table which is given to us? So, let us first define the given linear programming problem. This we had done in the last lecture also, but I am repeating it for the sake of continuity. We want to minimize Cx, which is subject to Ax less than or equal to b, x greater than or equal to 0. C is the coefficients of the objective function, A is Aij, b is bj, and x is the unknown parameters, that is x1, x2, xn. The sensitivity analysis is nothing but the effect of the change in the input data onto the final optimal table. So, this is the definition we had given for the sensitivity analysis as defined last time. Now, we have to look at the various other possibilities that could exist. We had in the last lecture looked at the variations in the values of CIs, that is the cost coefficients. We had also looked at the possibilities of variation in the right hand side, that is the BJs. Now, in today's lecture we will study the changes in the values of Aij. These are the coefficients of the constraints that exist in the problem. Then we will also look at the situation where we want to introduce a new variable into the problem. Thirdly, we want to look at a situation where we would like to introduce a new constraint into the problem. Fourth, we would like to look at the situation when we would like to delete a particular variable from the problem. And finally, we would like to look at what happens if we want to delete some constraint. So, in this lecture we will cover all these 5 possibilities. Now, the example that we had taken in the first part, let us read that again. I am taking particularly the same problem so that the continuity is maintained. So, the problem is that a company plans to produce 3 of its products, let us say A, B and C. The unit profit on these products is given to be rupees 2, rupees 3 and rupees 1 respectively, and they require 2 resources, that is labor and material. The company's OR department has formulated the following problem for determining the optimal mix. We will assume that the 3 variables x1, x2, x3 are the number of units to be produced of the 3 products, that is A, B and C. We want to maximize the profit, which is given by z is equal to 2x1 plus 3x2 plus x3, and there are two constraints of the problem. One is corresponding to the labor, which is given by 1 upon 3 x1 plus 1 upon 3 x2 plus 1 upon 3 x3 less than or equal to 1, and the second constraint is corresponding to the material, and it is given by 1 upon 3 x1 plus 4 upon 3 x2 plus 7 upon 3 x3 is less than or equal to 3, and x1, x2 and x3 should be greater than or equal to 0. Now, as in the last lecture, the initial and the final table can be seen as in this table. In the initial table, we have the bases given by x4 and x5, and under the x1 column we have 1 by 3, 1 by 3. Under x2 we have 1 by 3, 4 by 3. Under x3 we have 1 by 3, 7 by 3. Under x4 we have 1, 0, and under x5 we have 0, 1, and the right hand side is 1, 3. Now, since the coefficients of x4 and x5 is 0 in the objective function, therefore, in the first column we need to write the value 0, 0. On the top row we have the coefficients of the objective function, that is 2, 3, 1, 0 and 0. Now, we will calculate the deviation entries, and they are the same, that is 2, 3, 1, 0 and 0. This is the initial table. Now, coming to the final table, in the final table we have the bases x1 and x2, and the corresponding coefficient of x1 and x2 in the objective function is 2 and 3. So, it goes to the first column, and we have the columns under x1, x2 etc. 1, 0, 0, 1, minus 1, 2, 4, minus 1, minus 1, 1 and 1 and 2. And the objective function value, that is the cost, that is the profit, that is equal to 8. And the deviation entries in the final table are 0, 0, minus 3, minus 5 and minus 1. So, this is the initial and the final table that is sort of given to us. Now, we want to look at the variations in the A, that is the AIJs. Now, if you want to, if you try to look at this carefully, there arises three cases. In case number 1, we can consider adding new variables or activities, that is more and more variables. What happens, we want to see what happens if more and more variables are introduced into the problem. Second case is changing the resource requirement of the existing activities, and the third is adding new constraints. So, what does it mean? Let us look at each of the cases one by one. In the case number 1, we will talk about adding new variables or activities into the problem. What does this mean? Suppose in our given problem, it is proposed to produce a new product which we will call as D, and it is given that this product D requires 1 unit of labor and 1 unit of material respectively, and has a profit of rupees 3 per unit. So, we want to see whether it is beneficial to produce D or not. That is the question we have to answer. Therefore, the question is it economical to produce D or not? Now, the answer to this question leads us to the fact that we need to introduce a new variable into the problem. A new variable has to be introduced into the problem. Now, how do we introduce a new variable? Now, a new variable, let us call it x6, because already we have 5 variables. x1, x2, x3 are corresponding to A, B and C, and x4 and x5 are the slack variables. So, let us use x6 as a variable which is corresponding to the new activity, or rather new variable, new product. So, a new variable x6 has to be introduced by adding a new column, that is, what is this new column? 1 1 in the initial table. Now, why is it 1 1? It is 1 1 because 1 is corresponding to the first resource, that is labor, and the second one is corresponding to the material. It is given in the problem that if D has to be produced, then D requires 1 unit of labor and 1 unit of material. Therefore, this column vector 1 1 will have to be introduced into the initial table. After doing that, we will now calculate the simplex multipliers, and as before, the simplex multipliers are nothing but pi is equal to CB B inverse. Now, you know what is CB? CB is the coefficients of the variables, the basic variables in the objective function. So, CB is nothing but 2 and 3, and B inverse is the matrix 4 minus 1 minus 1 1, and if you multiply the 2, you will get a row vector which is given by 5 1. Now, corresponding to the variable x6, the entry in the deviation rows have to be calculated. So, all the other entries are already there except C6 bar. So, we will calculate C6 bar, which is given by C6 minus pi times P6. What is C6? C6 is 3. Why it is 3? It is given in the problem. It is given in the problem that the product D will have a profit of rupees 3 per unit. Therefore, this 3 comes from the given data, right, minus what is pi? Pi we have just now obtained is the simplex multipliers 5 1 and then multiplied by 1 1, that is the column vector corresponding to this new variable, and if you multiply this, you will get minus 3. As you know, minus 3 is less than 0, and this indicates that if you produce D, then it will not increase the profit. The profit will remain as it is, means the problem will remain optimum and it will have the same solution as the original problem. Therefore, producing D will not increase the profit. Now, on the other hand, it might not be so always. Suppose C6 is C6 bar is greater than 0, right? Then that means the problem, the solution is not optimum any longer. So, suppose it is proposed to produce a product, let us say D, which requires 2 units of labor and 3 units of material and has a profit of rupees 15 per unit. So, all the data has changed. Again, let us calculate C6 bar, which is given by C6 minus pi times pi 6, that is given to be as 15 minus 5 1 multiplied by 2 3, this comes out to be 2. Now, 2 is greater than 0. This indicates that the problem is the solution is no longer optimum. So, the table is no longer optimum, and therefore, the simplex method has to be applied afresh. You have to apply the simplex calculations afresh. Let us do it. How we will do it? If you look at this table, this x4 and x5 are already there, 1 by 3, 1 by 3, 1 by 3, 4 by 3, 1 by 3, 7 by 3, 1 0, 0 1. This is all, this is the initial table that we have been given in the problem. Now, we will like to add 2 3 over here, because this is the new data that has been given, and 15 is the profit. So, on the top we have to write 15 and the right hand side is 1 3. So, the last column of the, rather last but one column has to be added into the initial table. Now, we have to perform the simplex calculations all over again, and this means we have to look at the deviation entries. So, if you look at the deviation entries, you get 2, 3, 1, 0, 0 and 15. And what does this mean? This means that 15 is the largest. So, therefore, the x6 variable should enter the basis, and then we will perform the minimum ratio test, and we find that 2 is the pivot. Accordingly, we will apply the elementary row operations and get the second iteration as follows. In the first column we will write 15 0, second column we will write x6 and x5, then next column 1 by 6 minus 1 by 6, 1 by 6 5 by 6, 1 by 6 11 by 6, 1 by 2 minus 3 by 2, 0 1, 1 0, and finally right hand side is 1 by 2 and 3 by 2. Again we will need to calculate the deviation entries. They are nothing but minus 1 by 2, 1 by 2, minus 3 by 2, minus 15 by 2, 0, 0, and the cost Z is equal to 15 by 2. Now, we find that there is one entry in these deviation rows which is not less than 0, which indicates that this variable should enter into the basis. And after applying the minimum ratio test, we find that 5 6 is the pivot element. Accordingly, we need to apply the elementary row operations, and we get the third table as follows. In the first column we have 15 3, second column we have the basis as x6 and x2, then we have 1 by 5 and minus 1 by 5, 0 and 1, minus 1 and 5, 11 by 5, 4 by 5, minus 9 by 5, minus 1 by 5, 6 by 5, 1, 0, 1 by 5, 9 by 5, and similarly the deviation entries minus 2 by 5, 0, minus 13 by 5, minus 33 by 5, minus 3 by 5, 0, and the value of the objective function as 57 by 5. So, what does this mean? This means that the solution now is optimum because all the entries in the deviation rows is negative or 0. This indicates that the solution which is now obtained, the new solution is x2 is equal to 9 by 5, x6 is equal to 1 by 5, all others as 0, and z is equal to 57 by 5. Next, let us look at case 2. In the case 2, we want to see what happens when the changing resource requirement of the existing activity takes place. That is, in case of the non-basic variable, let us say for example product C, we have to apply the same steps as that of case 1. However, in case of basic variable, for example product B, we have to solve the LPP again. No other alternative is possible. Case 3, adding new constraints. Now, suppose products A, B and C require 1, 2 and 1 hour of administrative services. So, as you know, there were earlier there were only two conditions. One was corresponding to the labor and the other was corresponding to the material. Now, we have a third constraint which is corresponding to the administrative services. So, when we introduce this third constraint, the available service of this administrative service is 10. So, all this data can be clubbed together in the form of a third constraint as follows: x1 plus 2x2 plus x3 less than or equal to 10. And now, we want to see if the optimum solution which has been obtained till now satisfies these constraint or not. So, let us substitute this the solution obtained into this equation, and what do we get? 1 plus 2 multiplied by 2 plus 0 is less than or equal to 10. In this case, it is satisfied. Therefore, what do we conclude? We conclude that if we add this additional constraint into the problem, then our solution will remain the optimum. The solution will remain the optimum. There will be no change in the solution. Now, on the other hand, if this does not happen, then what to do? If it does not satisfy the new constraint, that is, the solution does not satisfy the new constraint, then we need to add a new row and solve the LP again, okay, because the new constraint has to be incorporated in the initial table itself, and therefore, once we do that, then we have to solve the entire problem again. For example, if we have this new constraint x1 plus 2x2 plus x3 less than or equal to 4. So, the problem becomes as before, we have to maximize the profit. Z is equal to twice x1 plus 3x2 plus x3 subject to 1 by 3 x1 plus 1 by 3 x2 plus 1 by 3 x3 less than or equal to 1, that is the labor requirement. Second constraint is 1 by 3 x1 plus 4 by 3 x2 plus 7 by 3 x3 less than or equal to 3. This is the material constraint, and the new constraint that we have added regarding the administration is given by x1 plus 2x2 plus x3 is less than or equal to 4. All the variables x1, x2 and x3 should be greater than or equal to 0. Now, what we have to do? We have to solve the problem again. There is no other alternative. Next, let us look at what happens if we want to delete a variable. So, if the deleted variable is non-basic variable or a basic variable with a 0 value in the optimum basis, then the original optimum solution remains unchanged, because the 0 value of the variable in the optimum solution makes the variable non-existent in effect. So, that is very straightforward. Now, let us look at the initial and the final table again. So, this is the same table that we have seen in the beginning of the lecture. I have just shown it again just to indicate the initial and the table and the final table entries. Now, if you look at this initial and final table, there are a couple of observations. For example, the optimum solution is given by x1 is equal to 1, x2 is equal to 2, x3, x4, x5, all the 3 are equal to 0. Suppose we want to delete x3, that is x3 has to be deleted. Now, it is a non-basic variable with 0 value. It is a non-basic variable with 0 value. So, its deletion will not affect the optimum solution. On the other hand, if the variable to be deleted is a basic variable with positive value in the optimum solution, then from the original optimum table, delete the column corresponding to the deleted variable. Also, the variable should be dropped from the basis column. This leaves the equation against the deleted basic variable in a form which is not canonical, and the number of basic variable in the system 1 short, that is 1 less. Now, introduce an artificial variable in this equation and proceed to obtain the solution by the two-phase or the big M method. So, that is the way it has to be done. Let us take an example. Now, the optimum solution is x1 is equal to 1, x2 is equal to 2, x3, x4 and x5 is equal to 0. Now suppose x2 has to be deleted. So what do? We look at this column x1, x2, x3, x4, x5. This is the initial table, and since x2 has to be deleted, I have placed a cross at this column, at this second column. So this column has to be deleted, and correspondingly this variable in the basis x2 has to be deleted, right. So the problem becomes maximization of z is equal to twice x1 plus 3x2 plus x3 subject to x1 minus x3 plus x4 minus x5 is equal to 1, 2x3 minus x4 plus x5 is equal to 2, and adding an artificial variable, let us say x6 in the second constraint, we get the new second constraint as twice x3 minus x4 plus x5 plus x6 is equal to 2. And what do we need to do? We need to solve this problem by the two phase method. Next comes the deletion of the constraint. Now, if the constraint to be deleted is such that its slack variable has a positive value in the optimum solution, then the deletion leaves the optimum solution unchanged. For example, the slack variable of the second constraint is x5 and x5 is equal to 1, which is greater than 0. So its deletion will leave the optimum solution unchanged. If the constraint to be deleted has 0 value for its slack variable in the optimum solution, that is, if it is being satisfied as an equality, then the modified problem may have a different optimum solution, and therefore it has to be solved again. Now let us look at the effect of the simultaneous changes in the value of the input parameters. Now suppose you have to make changes simultaneously in many parameters, then make these changes sequentially, that is one after the other, by taking one type of a change at a time. Since the problem is linear and the cumulative effect of these sequential changes will be the same as that of carrying out all these changes simultaneously. In case there are too many changes in the input data, it is usually preferable to solve the modified problem all over again. So finally, we will look at an exercise, and I would like you to solve this exercise as a homework. The problem is maximization of f is equal to x1 minus x2 plus 2x3 subject to x1 minus x2 plus x3 is less than or equal to 4, x1 plus x2 minus x3 is less than or equal to 3, twice x1 minus twice x2 plus 3x3 is less than or equal to 15, and all xi's are greater than or equal to 0. Assuming x4, x5 and x6 respectively as the slack variables to the 3 constraints, the optimum solution is given in the following table. Now, this is a table that is given. I think this is the same table as in the previous lecture. You have to carry out the sensitivity analysis for each of the following changes. Number 1, coefficient of x2 and x3 change to the following, that is C2 is equal to -2, A12 is equal to 2, A22 is equal to 3, A32 is equal to -1. Similarly, C3 is equal to 1, A13 is equal to 3, A23 is equal to -2 and A33 is equal to 1. Secondly, first constraint is to be deleted. The third part is a new constraint is to be introduced, and that constraint is given by twice x1 plus x2 plus 2x3 is less than or equal to 60, and finally the fourth part is the third constraint becomes 4x1 minus x2 plus 2x3 is less than or equal to 12. Now, each of these 4 parts have to be done one at a time and not simultaneously. Thank you.